Now Kirchhoff's laws. So these laws are also one of the basic and very important laws. Okay. So you have two Kirchhoff's laws. The first one is the Kirchhoff's current law. It is often abbreviated as KCL. So remember this as well. We are going to use KCL only in the future. Okay. So Kirchhoff's current law is based on the law of conservation of charge. Based on law of conservation of charge. Okay. So what was the law of conservation of charge? Charge can neither be created nor it can be destroyed. So according to Kirchhoff's law, the algebraic sum of currents entering or leaving a node is 0. Okay. So this is the law. Now here we need to understand one term, which is node. What is meant by a node? So a node is nothing but a connecting point between two or more circuit elements. For example, here you have a resistor and here you have another resistor. Then this point is the node. Okay. So why it is called a node? Because it is connecting two circuit elements. Connecting point of two or more circuit elements. Okay. For example, another example, if you take, there is a voltage source. Here you have a resistance and here you have a resistance. Okay. So this is one node, two circuit elements are being connected. This is another node, three circuit elements are being connected. And this is also one node. Okay. So this is what is meant by a node. Now what does Kirchhoff's current law states? KCL, it states that algebraic sum of currents entering or leaving a node is 0. That means, if, for example, if you take the current through this as I1, I2 and I3, okay, then the algebraic sum is 0. Okay. For the currents that are entering, we will take one polarity, and for currents leaving, we will take the other polarity. Okay. So for example, I1 we take as positive, it is entering. I2 and I3 are leaving, so we take as minus I2 minus I3. Okay. So that's why we call it as the algebraic sum, because we use the appropriate sign, and this is equal to 0. This is one way of looking at KCL. Another way of looking at it is, you can just say that the sum of currents entering is equal to the sum of currents leaving. Okay. Or sum of currents entering a node is equal to sum of currents leaving the node, the same node. Okay. So in this example, if you see, what is the currents entering? Only one current, which is I1, right? So I1 is equal to, what is the currents that are leaving? I2 and I3. So I2 plus I3, sum of currents leaving. So you can see that both these relations are one and the same. So this is what is the Kirchhoff's current law. One more important point in KCL is that you don't only have to take one node. You can take a entire region. Okay. For example, we'll take another circuit. Let us say there is a resistance coming like this. There is a resistance, there is a voltage source, let us say, something like this, and here you have some circuit element. Here you have another current source, let us say, and you can take another resistance. Okay. Now let us say if you take this entire set. Okay. Now this entire set you can consider as one single node, so that if current that is entering here is I1, here I2, here I3, and here let us say this current source is giving I4 current. Okay. Now the KCL can be applied for this entire region as well, because whatever is going into a particular region, it should come out of that. Okay. So it need not be a node only, it can be a collection of elements, it can be a collection of nodes. Okay. So what is the KCL here? The sum of currents entering is only I1, but the 3 currents are leaving I2, I3 and I4. So I2 plus I3 plus I4. Okay, so KCL can be applied for these kind of circumstances as well. The second Kirchhoff's law is the Kirchhoff's voltage law. Okay, so Kirchhoff's current law was based on the law of conservation of charge, and Kirchhoff's voltage law, which you can abbreviate as KVL, this is based on law of conservation of energy. What is law of conservation of energy? Energy can neither be created nor it can be destroyed. So what does this law state? It states that the algebraic sum of voltages, algebraic sum of voltage around a closed path is 0. Okay. So why is that the case? If you take a closed loop, there are a lot of circuit elements in between. Okay. Now if you start a charge at this point and you are moving it all through the loop and you're getting it back to the same position, then what is the work done? When there is no change in displacement, the work done is 0. You can remember the mechanical work, right? When what is mechanical work? Integral f dx. Integral f dot dx, right? And when there is no displacement, then the work done is 0. Similarly, in the electrical circuits, you take a charge and you're moving it like this, there is no net displacement, then what will happen to the work done? The work done is simply 0. Now what is voltage? Voltage is nothing but the work done, right? Work done in moving a charge. So when the work done is 0, that means the voltage, if you take around the closed loop, then it should be 0. Okay. So if you take we'll take a circuit. Let us say there's a voltage source here. There is some circuit element. The circuit element, if I draw a box, it means that it can be a resistance, capacitance, it can be anything. Okay. You can draw resistors as well if you are more comfortable like that. And here you have a dependent source. Okay. Now let us say the voltage given by this source is V1, this source is V4, and here we can take V2 and V3 like this. Now how do we apply the KVL? We will take a specified direction. So here we are taking the clockwise direction. Okay. So what we will do, each time we encounter a positive polarity, we will write with the positive sign. That means V2. And when you go like this, V3 is also positive, V4 is positive, but when you're going like this, V1, first you are encountering negative. So V1 you can take as negative. So minus V1 plus V2 plus V3 plus V4 is equal to 0. Okay, as simple as that, nothing else. This is the KVL. Okay, you have to take a specified direction and then you have to start writing the voltage values along with their sign. How do you write the sign? When positive is encountered first, it is first encountered, then you will take a positive polarity is first encountered, then you will take a positive sign. Okay. If negative polarity is first encountered, then you take the negative sign. Okay. You can use other way also. If positive, like it all depends on how you want to take it. Okay. And here you have taken a clockwise direction. You can take counterclockwise also. What matters is all of the polarities, see when you go like this, positive, positive, positive. So all of this should be of the same sign. Whether they are positive or negative is different. V1 should be different as compared to these three. That is the only thing here. Okay. Now this is a simple loop that we have taken. There's only one loop here. Now for example, let us say you have something like this. You have a circuit element here. There's a circuit element here. And here you have another circuit element. Here you have a current source, let us say. Okay. Now you can apply the KVL across this loop as well as this entire loop also you can apply. Okay. For example, if you have voltage V1 here, polarities are important always. Without polarities you cannot write. So this is the thing, let us say. So this is, let us say, V5. Then if you want to apply KVL in only loop, this smaller loop 1, okay, then what will be the KVL here? Minus V1 plus V2 plus V5 is equal to 0. And what about the bigger loop? If you apply for the entire both of the loops, composite loop you can say. So what will that be? Minus V1 plus V3 plus V4 is equal to 0. Okay. So it can be applied in this manner also.